welcome to a journey through 100 mysterious facts about the Milky Way Galaxy. Over the next 2 hours, we'll explore our cosmic home, from its supermassive black hole to the spiral arms where stars are born. Whether you're here to fall asleep, to study, or simply to relax while learning about the universe, sit back, take a deep breath, and let the wonders of our galaxy unfold. The Milky Way is more than just a beautiful band of light across the night sky. It's a complex cosmic city, home to hundreds of billions of stars, countless planets, and structures we're only beginning to understand. From the ancient black hole at its heart to the faint stars in its distant halo, every part tells a story of cosmic evolution spanning nearly 14 billion years. Let's begin our gentle journey through the Milky Way. The Milky Way gets its name from its appearance in the night sky. To ancient cultures around the world, the pale band of light stretching across the darkness looked like spilled milk flowing through the heavens. The ancient Greeks called it Galaxia's Kyklos, meaning milky circle. The Romans called it Via Lactea, the road of milk. In Sanskrit, it was known as Akash Ganga, the river of light. This ancient name has persisted through thousands of years of human civilization, reminding us of humanity's long relationship with the stars above. Every culture that has looked up at a dark sky has noticed this mysterious band of light and wondered about its nature. The Milky Way is classified as a barred spiral galaxy, designated SBBC in astronomical notation. This means it has a central bar-shaped structure made of stars, with spiral arms extending outward from the ends of the bar. For many years, astronomers debated whether our galaxy had this bar structure. It wasn't until detailed infrared observations in the early 2000s that we confirmed the presence of this stellar bar at the heart of our galaxy. The bar is approximately 27,000 light-years long and rotates as a single rigid structure, channeling gas toward the galactic center and influencing star formation throughout the galaxy. The Milky Way measures approximately 100,000 light-years from edge to edge. To put this in perspective, light travels at 300,000 kilometers per second, fast enough to circle the Earth 7.5 times in just 1 second. Even at this incredible speed, light takes 100,000 years to cross our galaxy from side to side. If you could somehow travel at the speed of light, you would grow old and die many times over before completing the journey across the Milky Way. The galaxy is so vast that it contains enough space for hundreds of billions of stars, each separated from its neighbors by distances measured in light years. While the Milky Way stretches 100,000 light years across its disk, it's relatively thin, only about 1,000 light years thick in most places, though the central bulge extends further. This gives our galaxy the appearance of a cosmic pancake or frisbee. Imagine a dinner plate that's 100 meters wide, but only 1 meter thick. That's roughly the proportional shape of our galaxy. This flat disk structure is the result of angular momentum. As the galaxy formed from a rotating cloud of gas, material settled into a spinning disk, much like pizza dough spun by a chef flattens into a circular shape. The Milky Way contains between 200 and 400 billion stars. This number is so vast, it's almost impossible to comprehend. If you tried to count every star in our galaxy, counting one per second without stopping, It would take you over 6,000 years to finish. And that's just our galaxy, one of hundreds of billions in the observable universe. Each of those stars is a sun, potentially with its own system of planets, moons, asteroids, and comets. The diversity of stellar types, sizes, and ages creates an incredibly complex galactic ecosystem. Our solar system resides in a minor spiral arm called the Orion Spur, also known as the Orion Arm or local arm. This spur is situated between the larger Perseus and Sagittarius arms. We're located about 26,000 light-years from the galactic center, roughly halfway out from the core to the outer edge. This suburban location, neither too close to the dangerous and chaotic galactic center, nor too far out in the barren outer regions, may be one reason life was able to develop on Earth. Our location provides a relatively stable environment, free from the intense radiation and frequent supernova events that characterize the inner galaxy. The Milky Way is approximately 13.6 billion years old. This means our galaxy formed only about 200 million years after the Big Bang itself, making it nearly as old as the universe. The oldest stars in our galaxy, found primarily in globular clusters and the stellar halo, are almost 13 billion years old. These ancient suns have witnessed the entire history of galactic evolution. They were shining when the first galaxies were forming, when the universe was still young and different from the cosmos we see today. The Milky Way rotates, but not like a solid wheel or disk. Different parts rotate at different speeds, a phenomenon astronomers call differential rotation. Near the galactic center, stars complete an orbit in just a few million years, whipping around the central black hole at tremendous speeds. Out where we are, approximately 26,000 light-years from the center, it takes the Sun approximately 225 to 250 million years to complete one orbit around the galactic center. This orbital period is sometimes called a cosmic year or galactic year. Right now, as you listen to this, you're moving through space at incredible speeds. The Earth orbits the Sun at about 30 kilometers per second, over 100,000 kilometers per hour. The Sun, along with the entire solar system, orbits the galactic center at approximately 220 kilometers per second, nearly 800,000 kilometers per hour. And the entire Milky Way itself is moving through space at around 600 kilometers per second relative to the cosmic microwave background radiation, the afterglow of the Big Bang. You are on a cosmic journey through space at speeds that would make any spacecraft seem frozen in comparison. Yet you feel none of this motion because everything around you is moving together. From our position inside the Milky Way, we can never see it the way we see other galaxies. We're trapped inside the disk, looking through the stars, gas, and dust that make up our galaxy. It's like trying to understand the layout of a city while standing in the middle of a crowded street on a foggy day. Everything we know about the Milky Way structure comes from careful observation, measurement of star positions and velocities, study of gas and dust clouds, and comparison with other similar galaxies we can see from the outside. Astronomers have painstakingly pieced together a map of our galaxy using radio, infrared, and visible light observations, but we'll never have the perspective of viewing it from a distance. The distance across the Milky Way, 100,000 light years means that light from one side of the galaxy takes 100,000 years to reach the other side. If you could somehow watch our galaxy from the outside, you wouldn't be seeing it as it exists at a single moment in time. You'd be seeing different parts at different times, like watching a very slow cosmic movie where different scenes play out across the galactic disk. The center would appear as it was 26,000 years ago, while the far side would be visible as it existed 126,000 years in the past. Even traveling at light speed, the fastest possible speed in the universe according to Einstein's theory of relativity, crossing the Milky Way would take 100,000 years. This means that even with theoretical faster-than-light travel, which physics suggests is impossible, exploring even our own galaxy would take many, many human lifetimes. The distances involved in space are so vast that they fundamentally challenge our concepts of travel, exploration, and even communication. A radio signal sent to the far side of the galaxy would take 100,000 years to arrive, and the reply would take another 100,000 years to return. To understand the scale difference between our solar system and our galaxy, consider this. The entire solar system, out to the orbit of Neptune, is about 0.001 light years across, just 6 billion kilometers. The Milky Way is 100,000 light years across. Our entire solar system is a tiny, almost invisible speck compared to the enormity of our galaxy. It would take 100 million solar systems placed side by side to span the Milky Way. And yet, within that vast expanse, individual stars are still separated by such enormous distances that the galaxy is mostly empty space. Most of the Milky Way's stars, gas, and dust are concentrated in a relatively flat plane about 1,000 light years thick. Above and below this plane, star density drops dramatically. You can think of it like a thin layer of coins scattered across a vast table. This is why the Milky Way appears as a band across the night sky. We're looking along the plane of the disk, seeing the accumulated light of billions of stars stretched across our view. When we look above or below the galactic plane, we see relatively few stars and can observe distant galaxies beyond our own. At the center of the Milky Way is a roughly spherical bulge of densely packed stars, approximately 10,000 light years in diameter. This central bulge contains some of the galaxy's oldest stars, packed together much more tightly than stars in the disk. In the bulge, stars can be separated by only a few light weeks or light months, compared to the 4.2 light years to our nearest stellar neighbor, Proxima Centauri. If Earth were located in the galactic bulge, the night sky would be ablaze with thousands of bright stars, many brighter than any star we see in our current sky. Surrounding the visible disk and bulge is a vast, roughly spherical halo of dark matter, old stars, and globular clusters that extends perhaps 130,000 light years or more from the galactic center. This halo is mostly invisible to our telescopes. We detect it primarily through its gravitational effects on the rotation of the galaxy. The dark matter halo may contain as much as 90% of the galaxy's total mass, yet we can see almost none of it. It's like the galaxy we can see is just the tip of an enormous, invisible iceberg. If you could travel at 1 million kilometers per hour, far faster than any spacecraft we've ever built, it would still take you over 100 billion hours to cross the galaxy. That's over 11 million years of continuous travel, even at 1% the speed of light, which would require technology far beyond our current capabilities. Crossing the Milky Way would take 10 million years. To give some perspective, humans have existed as a species for only about 300,000 years. The galaxy is not just large, it is vast beyond our everyday experience or intuition. The Milky Way has a total mass of approximately 1.5 trillion times the mass of our Sun. Most of this mass, perhaps 90% or more, is in the form of dark matter, invisible material that we can only detect through its gravitational effects. The visible stars, gas, and dust that make up the galaxy, we can see account for only a small fraction of the total mass. The rest is dark matter, one of the greatest mysteries in modern astronomy. We don't know what dark matter is made of, but we know it's there because of how it affects the motion of stars and gas in the galaxy. In our neighborhood of the galaxy, there is roughly one star per 300 cubic light years of space. This means that stars are incredibly far apart relative to their size. If the Sun were the size of a grain of sand, the nearest star would be another grain of sand about 10 kilometers away. Space is not crowded with stars. It is almost entirely empty, with tiny points of light separated by vast distances of nothing. This is why science fiction's depictions of spacecraft dodging through fields of stars are so unrealistic. Stars are much too far apart for such encounters. The Milky Way doesn't have a sharp edge where it suddenly stops. Instead, it gradually fades away, with star density decreasing as you move outward from the center. The exact diameter of the galaxy depends on where you decide to call the edge. Some definitions place it at 100,000 light years when considering the main disk. Others place it at 150,000 or even 200,000 light years when including the outermost stars and star clusters in the stellar halo. And if you include the dark matter halo, the galaxy may extend even further into space, perhaps several 100,000 light years from the center. The Milky Way has 4 major spiral arms that wind outward from the central bar: the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the outer arm, sometimes called the Norma arm. These arms are regions of higher star density that wind outward from the galactic center in a graceful spiral pattern. They're not solid structures like the arms of a pinwheel, but rather waves of higher density moving through the galaxy, like ripples spreading across a pond. The arms rotate more slowly than the stars themselves, so individual stars move in and out of spiral arms during their orbits around the galaxy. Our solar system resides in the Orion Spur, also called the Orion Arm, Orion Bridge, or Local Arm. This is a minor arm or spur between the larger Perseus and Sagittarius arms. It's about 3,500 light years wide and approximately 10,000 light years long. We're located in a relatively calm, stable region of the galaxy, not in the dense, chaotic environment of a major spiral arm with its frequent supernova and intense star formation, which may have been important for the development and survival of life on Earth. Sometimes the safest place is away from the action. At the heart of the Milky Way is a bar-shaped structure made of stars, approximately 27,000 light years long and about 3,000 light years thick. This bar rotates as a roughly rigid structure, completing a full rotation every 200 million years or so. The bar's gravitational influence is significant. It helps channel gas from the outer galaxy toward the galactic center, triggering star formation. The bar may also affect the structure of the spiral arms. About 2/3 of all spiral galaxies have these bar structures, and astronomers believe bars form and dissolve over cosmic timescales, playing an important role in galactic evolution. Spiral arms are not permanent, static structures. They're density waves, regions where stars, gas, and dust temporarily bunch together as they orbit the galactic center. It's similar to a traffic jam on a highway. The jam moves slower than the individual cars, and the cars enter the jam from behind, slow down, then speed up again as they exit. Individual stars move in and out of spiral arms as they complete their orbits around the galaxy. The arms persist over millions of years because new material is constantly entering them, even as old material leaves, maintaining the wave pattern. Spiral arms are sites of vigorous star formation. As giant molecular clouds of gas enter a spiral arm, they're compressed by the increased density and gravitational forces, triggering the collapse of the gas into new stars. This is why spiral arms appear bright and blue in photographs. They contain many young, hot, blue stars that formed recently and haven't lived long enough to drift away from their birthplace. These massive blue stars live only a few million years before exploding as supernovae, so they remain in the spiral arms where they were born, lighting up the arms like cosmic streetlights. The Milky Way's disk isn't perfectly flat. It's warped, bending up on one side and down on the other, like the brim of a cowboy hat or a slightly bent vinyl record. This warp becomes more pronounced toward the outer edges of the galaxy, where the disk can be displaced by several thousand light years from the central plane. The cause of this warp isn't completely understood. It may be due to gravitational interactions with satellite galaxies like the Magellanic Clouds, the influence of dark matter in the galactic halo, or the effects of past galactic collisions. Many spiral galaxies show similar warps in their outer disks. The Milky Way actually has two overlapping disk components. There's the thin disk, about 1,000 light-years thick, containing most of the stars, gas, and dust we see. But there's also a thick disk extending to about 3,000 light-years above and below the galactic plane. The thick disk contains older stars with different chemical compositions and orbital characteristics compared to thin disk stars. These stars move in more elliptical orbits that carry them above and below the galactic plane. The thick disk may have formed earlier in the galaxy's history, or it may be the result of past interactions with smaller galaxies that were absorbed by the Milky Way. Orbiting the Milky Way in the galactic halo are approximately 150 known globular clusters, dense, spherical collections of very old stars. Each globular cluster contains hundreds of thousands to millions of stars packed into a region only 100 to 200 light-years across. In the densest central regions of these clusters, stars can be separated by only light days or light weeks, close enough that planetary systems might be disrupted by passing stars. These clusters orbit in the galactic halo, taking hundreds of millions of years to complete their highly elliptical orbits. Their extreme age, typically around 12 to 13 billion years, suggests they formed very early in the galaxy's history. The Milky Way isn't alone. It's accompanied by dozens of smaller satellite galaxies that orbit around it, held by our galaxy's powerful gravitational pull. The largest and most famous are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches in the night sky. These are dwarf irregular galaxies containing billions of stars. Closer and more difficult to detect are many ultra-faint dwarf galaxies, some containing only a few thousand stars. These satellites are being gradually torn apart by the Milky Way's gravity through a process called tidal disruption. Their stars slowly join our galaxy, adding to the Milky Way's stellar halo in long streams of stars. There's a region in the plane of the Milky Way, extending about 10 to 20 degrees above and below the galactic equator, where we have great difficulty observing distant galaxies. Astronomers call this the zone of avoidance. This region is blocked by the dense gas, dust, and stars of our own galaxy's disk. The dust absorbs visible light and obscures our view of the universe beyond. About 10 to 20% of the sky is affected, hiding countless galaxies behind the veil of the Milky Way. Astronomers use infrared, radio, and X-ray observations to peer through the dust and study what lies beyond. But the zone of avoidance remains a significant challenge in mapping the large-scale structure of the universe. As we move deeper into our journey through the Milky Way, we approach the mysterious heart of our galaxy, the galactic center, home to one of nature's most extreme objects, a supermassive black hole containing over 4 million times the mass of our Sun. This gravitational monster anchors our entire galaxy, and around it, the cosmic dance of stars and gas creates one of the most exotic environments in the known universe. The structure of our galaxy reveals itself slowly, like a puzzle assembled piece by piece over centuries of astronomical observation. Each discovery adds another layer to our understanding of this vast cosmic city we call home. The galactic disk contains most of the material we can see: stars, gas clouds, dust lanes, all concentrated in this relatively flat plane. But within this disk, there's remarkable complexity. The gas isn't uniformly distributed. Instead, it forms intricate structures, giant molecular clouds where new stars are born, expanding bubbles blown by stellar winds, and supernova explosions, shells and filaments tracing the paths of ancient explosions. These structures overlap and interact, creating a dynamic, ever-changing environment. The dust in the galactic disk, while making up less than 1% of the total mass, plays an outsized role in the galaxy's appearance and evolution. This dust, tiny grains of carbon, silicon, and other elements, absorbs and scatters starlight, creating the dark lanes visible in photographs of spiral galaxies. The dust also blocks our view of much of the galaxy when we observe invisible light. But this same dust radiates in the infrared, allowing infrared telescopes to peer through the obscuration and reveal hidden structures. Between the spiral arms lie the inter-arm regions, areas of lower stellar density and less active star formation. These regions are not empty, but they're quieter, more stable. Our solar system currently resides in such a region between the Perseus and Sagittarius arms. Here, the night sky is darker than it would be in a spiral arm. Massive stars are more distant. Supernova explosions are less frequent. This relative tranquility may have been important for Earth's development as a habitable world, providing billions of years of stability for life to evolve without catastrophic disturbances. The spiral pattern itself may be temporary on cosmic timescales. Computer simulations suggest that spiral arms can form, persist for 1 billion years or so, then dissolve, only to reform again later. The pattern we see today may not be the pattern that existed billions of years ago, and it may not be the pattern that will exist billions of years hence. The galaxy is not a static object frozen in time, but a dynamic, evolving system, constantly reshaping itself through the gravitational interactions of its components. Magnetic fields thread through the galactic disk, following the spiral arms and affecting the behavior of gas and charged particles. These fields are weak by everyday standards, about 1 million times weaker than Earth's magnetic field. But across the vast scales of the galaxy, they carry significant energy. They influence the collapse of gas clouds, affecting where and how stars form. They accelerate cosmic rays to incredible energies. They may even play a role in launching the winds and jets we observe, flowing out from the galactic center and from regions of intense star formation. Throughout the disk, gas is constantly in motion. Some gas orbits the galaxy in roughly circular paths, like the stars, but other gas is falling inward toward the center, channeled by the gravity of the central bar and spiral arms. Still other gas is flowing outward, pushed by stellar winds and supernova explosions. This circulation of gas, inward in some places, outward in others, is crucial to the galaxy's continued star formation and evolution. Without this gas flow, the galaxy would gradually consume all its available material and star formation would cease. At the very center of the Milky Way, buried behind thick clouds of dust and gas, lies Sagittarius A, pronounced Sagittarius A star. This is a supermassive black hole with a mass of approximately 4.1 million times that of our Sun. This black hole is the gravitational anchor of our entire galaxy, the point around which hundreds of billions of stars orbit. Despite its enormous mass, Sagittarius A is remarkably quiet compared to the supermassive black holes in many other galaxies, consuming relatively little material and producing relatively little radiation. Despite containing over 4 million solar masses, Sagittarius A has an event horizon, the point of no return around a black hole, only about 12 million kilometers in diameter. That's roughly 16 times the diameter of the Sun, or about the size of Mercury's orbit around our star. This means a mass equivalent to over 4 million suns is compressed into a region smaller than our inner solar system. The density at the center of the black hole is thought to be infinite, a gravitational singularity where the laws of physics as we understand them break down. Just outside the event horizon, space-time is warped to an extreme degree by the black hole's intense gravitational field. Astronomers have observed stars orbiting extremely close to Sagittarius A, providing some of the most direct evidence for the existence of the supermassive black hole. The star designated S2, also known as SO2, completes an orbit around the black hole in just 16 Earth years, bringing it within just 14 billion kilometers of the event horizon at closest approach. At these distances, S2 reaches speeds of up to 5,000 kilometers per second, about 1.6% the speed of light. By carefully tracking the orbits of S2 and other stars over many years, astronomers calculated the mass of Sagittarius A with great precision. These observations also provided some of the first tests of Einstein's general theory of relativity in the extreme gravitational environment near a black hole. The galactic center is located about 26,000 light-years away in the direction of the constellation Sagittarius. However, we can't see it with visible light telescopes because of the enormous amount of gas and dust in the way. This material absorbs and scatters visible light, making the galactic center completely opaque to our eyes and optical telescopes. The amount of obscuration is staggering. The dust blocks about 1 trillion times more light than a clear atmosphere. Astronomers study the galactic center using infrared, radio, and X-ray observations that can penetrate through the obscuring material. These observations have revealed a complex, dynamic environment, very different from the quiet region of space we inhabit. The central parsec, a region just 3.26 light-years across surrounding Sagittarius A, is one of the most extreme environments in the galaxy. Stars here are packed much more densely than in our solar neighborhood. There may be as many as 1 million stars within this small region. These stars experience intense tidal forces from the black hole's gravity. Some stars are on highly eccentric orbits that bring them perilously close to the event horizon. Collisions between stars may occur occasionally in this crowded environment. The radiation environment is also intense, with high-energy particles and strong ultraviolet and X-ray radiation from hot stars and gas falling toward the black hole. Surrounding Sagittarius A is a dense cluster of stars called the nuclear star cluster, containing approximately 10 million stars packed into a region only about 10 light-years in diameter. This is one of the densest stellar environments in the galaxy. If Earth were located in the nuclear star cluster, the night sky would be breathtaking and terrifying in equal measure. There would be thousands of stars brighter than Venus appears in our sky. The nearest stars might be only a few light months away. The sky would never be truly dark. This extreme environment would also pose challenges for life. Close supernova explosions would be more frequent, and planetary systems might be disrupted by passing stars. Sagittarius A occasionally produces X-ray flares, sudden brightenings in X-ray emission that last for a few hours. These flares occur a few times per day on average and can increase the X-ray brightness of the black hole by a factor of 10 to 100. The flares may be caused by material falling toward the black hole, perhaps asteroids or comets torn from orbits around nearby stars, or clumps of gas in the sparse accretion flow around the black hole. Despite these flares, Sagittarius AR is remarkably quiet compared to active galactic nuclei in other galaxies. Many supermassive black holes consume material at rates thousands or millions of times higher, producing enormous amounts of radiation and powerful jets of matter streaming away at nearly the speed of light. Extending 25,000 light-years above and below the galactic center are two enormous structures called the Fermi bubbles. These were discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. The bubbles are regions emitting high-energy gamma rays, visible in gamma ray images of the sky as two huge lobes extending above and below the galactic plane. Each bubble is about 25,000 light-years tall and 15,000 light-years wide, structures so vast they dwarf most features in the galaxy. The bubbles may have been created by past activity of Sagittarius A, perhaps a period millions of years ago when the black hole consumed a large amount of material and produced powerful jets and outflows. Alternatively, they might be the result of an intense burst of star formation in the galactic center, with the combined winds from millions of massive stars pushing material out of the galactic plane. The galactic center shows evidence of much more violent activity in the past. The Fermi bubbles, along with other structures like the X-ray plumes observed by the Chandra X-ray Observatory, suggest that within the last few million years, very recently in cosmic terms, the central regions of our galaxy were much more active. Sagittarius A may have been consuming material at a much higher rate, producing intense radiation and powerful outflows. There may have been a starburst, a period of extremely rapid star formation in the central regions, with massive stars forming and exploding in rapid succession. We may be living in a relatively quiet period of galactic history, with the evidence of recent violence still visible in the structures surrounding the galactic center. Our entire solar system orbits around Sagittarius A once every 225 to 250 million years, a period sometimes called a cosmic year or galactic year. We're traveling at approximately 220 kilometers per second on this galactic orbit. Since the Sun and solar system formed about 4.6 billion years ago, we've completed roughly 20 orbits around the galaxy. The last time we were at this point in our galactic orbit, the continents were in different positions, different life forms dominated Earth, and the night sky showed different constellations as our position relative to other stars changed. In another 230 million years, we'll return to this same location in our endless journey around the galactic center. Though Earth and the solar system will be very different places by then, new stars are born in giant molecular clouds, vast regions of cold gas and dust that can stretch hundreds of light years across and contain enough material to make millions of stars. These clouds are among the coldest places in the galaxy, with temperatures only a few degrees above absolute zero, colder than the space between galaxies. The Milky Way currently contains thousands of these stellar nurseries, scattered throughout its spiral arms and dense regions. The most famous ones have names like the Orion Nebula, the Eagle Nebula with its iconic pillars of creation, and the Carina Nebula. These are the birthplaces of stars, where gravity slowly compresses gas and dust until new suns ignite and begin to shine. The Milky Way creates approximately 1.5 to 3 new stars every Earth year. This might not sound like much, but over the galaxy's 13.6 billion year lifetime, even this modest rate adds up to hundreds of billions of stars. The birth rate has decreased over cosmic time. The galaxy formed stars much more rapidly in its youth, possibly creating dozens or even hundreds of stars per year during peak periods billions of years ago. Today's rate represents a relatively quiet phase of galactic evolution. Still, somewhere in the Milky Way right now, as you listen to this, new stars are being born from collapsing clouds of gas and dust. Some stellar nurseries produce massive star clusters containing thousands or even tens of thousands of stars, all born from the same cloud of gas at roughly the same time. These clusters begin as dense groupings in the molecular cloud, bound together by their mutual gravity. The young stars are so close together that their night skies would be filled with brilliant stellar neighbors. Over millions of years, many of these clusters gradually disperse as member stars drift apart, eventually scattering into the general stellar population. But some clusters remain bound for billions of years. The Pleiades, a famous cluster visible to the naked eye, contains over 1,000 stars formed about 100 million years ago and still traveling together through space. Sometimes star formation is triggered by external events rather than occurring spontaneously. When a massive star explodes as a supernova, the shock wave from the explosion compresses nearby gas clouds, potentially triggering the collapse that forms new stars. This means that stars can spawn future generations before they die, in a kind of cosmic inheritance. Similarly, the spiral density waves that create the galaxy's spiral arms compress gas as it enters the arm, triggering bursts of star formation. The passage of small satellite galaxies through the Milky Way's disk can also trigger waves of star formation, as the gravitational disturbance compresses gas clouds in their wake. Star formation is not a random process. It's influenced by the complex dynamics of the galaxy as a whole. When a molecular cloud collapses to form stars, it doesn't make equal numbers of stars at all masses. Instead, there's a strong preference for smaller stars. For every massive blue star formed, hundreds or thousands of smaller red and yellow stars are created. This distribution of stellar masses is called the initial mass function, and it appears to be remarkably similar wherever we observe star formation in the galaxy. The smallest stars, tiny red dwarfs with masses just a fraction of the Sun's mass, are by far the most common. These dim stars can live for trillions of years, far longer than the current age of the universe. None of the red dwarfs ever born have yet died of old age. The massive blue stars, while spectacular and dominating the appearance of star-forming regions, are relatively rare and short-lived, burning through their nuclear fuel in just a few million years. When stars form, they're typically surrounded by a disk of leftover gas and dust, a protoplanetary disk. In these disks, dust grains stick together, gradually building up larger objects. First tiny clumps, then pebbles, then rocks, then planetesimals, and finally planets. This process of planet formation appears to be common, perhaps even universal. Observations of young stars with powerful telescopes show that most have these disks, and studies of mature stars reveal that planets are extremely common throughout the galaxy. The Milky Way likely contains billions of planets, perhaps more planets than stars. Among these countless worlds, there are likely billions of Earth-sized planets orbiting in the habitable zones of their stars, where liquid water could exist on their surfaces. The Orion Nebula, visible to the naked eye as the middle star in Orion's sword, is one of the most active star-forming regions near our solar system, located about 1,300 light-years away. This glowing cloud of gas is illuminated by hot young stars that formed within it, their intense ultraviolet radiation causing the surrounding gas to fluoresce like a cosmic neon sign. The nebula contains enough material to make 2,000 stars, like the Sun. Observations with powerful telescopes have revealed hundreds of very young stars in various stages of formation, many surrounded by protoplanetary disks where planets are forming right now. The Orion Nebula gives us a window into the processes that occurred when our own solar system was born 4.6 billion years ago. Not all collapsing gas clouds become true stars. Sometimes, the collapsing core doesn't gather enough mass to ignite sustained hydrogen fusion in its core. These failed stars, called brown dwarfs, have masses between about 13 and 80 times that of Jupiter. They're not massive enough to fuse hydrogen like true stars, but the most massive brown dwarfs can fuse deuterium, a heavy form of hydrogen, for a brief period. Brown dwarfs glow faintly with infrared radiation from the heat of their formation and from limited deuterium fusion. They slowly cool over billions of years, gradually fading into darkness. The Milky Way may contain tens of billions of brown dwarfs, outnumbering true stars, but they're extremely difficult to detect because of their faintness. While the Milky Way creates about 2 to 3 new stars per year, stars are also dying at a similar rate. Low-mass stars like the Sun eventually swell into red giants and then shed their outer layers, leaving behind white dwarf remnants, dense stellar cores about the size of Earth. Massive stars meet more violent ends, exploding as supernovae and leaving behind neutron stars or black holes. The death rate roughly balances the birth rate, so the total number of stars in the galaxy remains relatively stable over time. However, the galaxy is slowly converting its gas into stars and stellar remnants, so the rate of star formation will gradually decline over tens of billions of years as the supply of gas is exhausted. When stars die, they return most of their material to the interstellar medium, the thin gas between stars. Red giants shed their outer layers in stellar winds, puffing off their envelopes over thousands of years. Supernovae explosively eject their contents into space in seconds. This returned material is enriched with heavy elements created by nuclear fusion in the star's core and, in the case of supernovae, by the explosion itself. Over time, the interstellar medium becomes enriched with these heavy elements. New stars form from this enriched gas, inheriting the chemical legacy of previous generations. The Sun and Earth are made largely from material that was once part of earlier generations of stars. We are, quite literally, made of stardust, atoms forged in the hearts of long-dead stars and scattered across space by their deaths. Approximately 90% of the Milky Way's total mass is in the form of dark matter, mysterious material that doesn't emit, absorb, or reflect light at any wavelength. We can't see dark matter with any telescope, regardless of what kind of radiation we observe. We only know it exists because of its gravitational effects on visible matter, the stars, gas, and dust we can see. Everything that makes up the beautiful images of the galaxy, all the glowing nebulae and brilliant star clusters, represents only about 10% of what's actually there. The rest is invisible, detectable only through its gravitational pull on the material we can see. Dark matter's existence was discovered through observations of how the galaxy rotates. According to Newton's laws of motion and gravity, stars far from the galactic center should orbit more slowly than stars closer in, just as outer planets in the solar system orbit the Sun more slowly than inner planets. But observations showed something unexpected. Stars far from the center move just as fast as stars closer in. The rotation curve, a graph of orbital velocity versus distance from center, is flat rather than declining as expected. This could only be explained if there's a large amount of invisible mass extending far beyond the visible disk, providing extra gravitational pull on the outer stars to keep them moving at higher speeds. Dark matter forms a roughly spherical halo around the visible galaxy. This halo extends perhaps 300,000 light-years or more from the galactic center, much larger than the visible disk. The dark matter isn't concentrated in the galactic plane like stars and gas. Instead, it's distributed more spherically, forming a vast, invisible cloud within which the visible galaxy is embedded. The exact shape and density profile of the dark matter halo is still being studied, as it's difficult to map the distribution of something we can't directly observe. Astronomers infer its structure from the motions of stars and gas and from computer simulations of galaxy formation. Despite decades of intensive research, we still don't know what dark matter is made of. It's definitely not made of atoms, the protons, neutrons, and electrons that make up ordinary matter. If it were, it would interact with the light, and we would be able to see it. Current leading theories suggest it may be composed of exotic particles that interact only through gravity and possibly through the weak nuclear force, but not through electromagnetism, which is why they don't emit or absorb light. Physicists have proposed various candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos, and other theoretical particles. Experiments around the world are searching for these particles, trying to directly detect them or create them in particle accelerators, but so far, direct detection has remained frustratingly elusive. Dark matter played a crucial role in the formation of galaxies in the early universe. In the first few 100 million years after the Big Bang, dark matter began clumping together under its own gravity, long before ordinary matter could. Dark matter doesn't interact with radiation, so it wasn't held back by the pressure of photons that prevented ordinary matter from collapsing. The dark matter formed gravitational wells, concentrations of mass, and ordinary matter fell into these wells, pulled by gravity. Galaxies formed within the dark matter halos, which provided the gravitational scaffolding for galaxy formation. Without dark matter, galaxies as we know them might not have been able to form. The visible galaxy is, in a sense, just the bright center of a much larger dark structure. Permeating the galaxy is a weak but extensive magnetic field. This galactic magnetic field is about 1/1,000,000th as strong as Earth's magnetic field, but it extends across the entire galaxy, threading through the spiral arms and connecting different regions. It's generated and sustained by the motion of electrically conducting gas in the galaxy, a process called the dynamo effect, similar to how Earth's liquid iron core generates our planet's magnetic field through its motion. This magnetic field affects the motion of charged particles, influences the collapse of gas clouds, and thus affects star formation, and shapes the structure of gas clouds and the distribution of cosmic rays throughout the galaxy. Streaming through the galaxy are cosmic rays, high-energy particles, mostly protons, traveling at nearly the speed of light. These particles carry tremendous energy, some individual particles having more kinetic energy than a thrown baseball, despite being just single atomic nuclei. These particles are accelerated to extreme energies, possibly by supernova shockwaves, pulsar winds, or other violent events. Cosmic rays are relatively rare, Only a few pass through your body each second, but they carry significant energy collectively. The galactic magnetic field traps and shapes the flow of cosmic rays, causing them to spiral along field lines, effectively confining them to the galaxy for millions of years before they eventually escape. Earth's atmosphere and magnetic field protect us from most cosmic rays, but they pose a radiation hazard to astronauts in space and can cause errors in electronic equipment, even at ground level. The space between stars is not truly empty. It's filled with the interstellar medium, a thin mixture of gas and dust. This medium has an average density of about 1 atom per cubic centimeter in most places, making it a better vacuum than anything we can create in laboratories on Earth, even with the most sophisticated equipment. Yet when integrated over the vast volumes of the galaxy, this incredibly thin medium contains about 10 billion solar masses of material, 10 billion times the mass of our Sun. The interstellar medium is the raw material for future star formation and the repository for material returned by dying stars. It's a complex, multi-phase medium with regions of vastly different temperatures and densities, from cold molecular clouds at 10 degrees above absolute zero to hot ionized gas at millions of degrees. Surrounding the galactic disk is a halo of hot, diffuse gas extending tens of thousands of light years above and below the plane. This gas has temperatures of millions of degrees, hot enough that atoms are completely ionized and the gas emits X-rays. The hot halo may contain as much mass as all the gas in the galactic disk, forming a vast reservoir of material that's largely invisible except in X-ray observations. This hot gas is likely heated by supernova explosions in the disk that send shockwaves upward by gravitational energy as the galaxy pulls in material from its surroundings, and by shockwaves from gas falling onto the galaxy. Understanding this hot halo is important for understanding the galaxy's past and future evolution, as it represents a reservoir of material that may eventually cool and fall back into the disk to form new stars millions of years hence. The Milky Way is held together by gravity, the mutual gravitational attraction between all its components. But within the galaxy, individual objects feel gravitational forces from many sources simultaneously. A star orbits in the combined gravitational field of all the matter closer to the galactic center than itself: stars, gas, and crucially, the dark matter that dominates the mass. Stars also feel the gravitational tug of nearby stars, passing molecular clouds, spiral density waves, and the central bar. These gravitational interactions are complex, creating intricate orbital patterns and driving the galaxy's evolution over cosmic timescales. Gravity is the fundamental force that shapes and maintains the structure we call the Milky Way, sculpting it continuously over billions of years. The Milky Way's spiral arms are named after the constellations, where they appear most prominent when viewed from Earth. The Perseus arm, named for the constellation Perseus, is one of the two major arms and lies outside our position in the galaxy. The Scutum Centaurus arm is named for the constellations Scutum and Centaurus and extends on the inner side of our location. The Sagittarius arm extends in the direction of Sagittarius, also interior to our position. The outer arm, sometimes called the Norma arm, traces the outer regions of the galaxy. These names reflect our Earth-bound perspective. Observers from other parts of the galaxy would see the arms differently and might name them something completely different. based on their own view of the galactic structure. Spiral arms persist for hundreds of millions or billions of years, yet individual stars pass through them in just a few million years during their orbits around the galactic center. How can the arms be long-lasting features if they're not made of the same stars over time? The answer lies in density wave theory, developed in the 1960s by astronomers C.C. Lin and Frank Xu. According to this theory, spiral arms are not material structures, but rather waves of compression moving through the galactic disk, somewhat like sound waves moving through air or ripples spreading across water. As stars and gas orbit the galaxy, they periodically pass through these density waves, bunching together temporarily before spreading out again. The wave pattern itself rotates more slowly than the material passing through it, so the pattern persists even as the material flows through it, continuously renewed. As gas clouds enter a spiral arm, they're compressed by the increased density and gravitational forces present in the wave. This compression can trigger the gravitational collapse of the clouds, initiating star formation. This is why spiral arms are traced out by bright young blue stars and glowing pink and red nebulae. These are regions of active starbirth, cosmic maternity wards where new suns are igniting. The massive blue stars formed in the arms are so short-lived that they explode as supernovae while still in or near the spiral arm where they were born, never living long enough to drift away. This creates a feedback loop. Massive stars form. They explode after a few million years. Their shockwaves compress nearby gas, triggering more star formation. Spiral arms are cosmic assembly lines for stars, continuously producing new generations. Spiral arms are about 3,000 to 4,000 light-years wide, vast regions even by galactic standards. Our Sun takes approximately 2 million years to cross through a spiral arm during its orbit around the galaxy. Our solar system is currently located in the Orion Spur, between the major Perseus and Sagittarius arms, so we're in a relatively less dense, quieter region. The last time our solar system was deep inside a major spiral arm, dinosaurs walked the Earth, and mammals were small creatures living in the shadows. The next time we pass through a major arm, tens of millions of years hence, the continents will have moved significantly, and if humanity or our descendants still exist, they may have spread far beyond Earth. These passages through spiral arms might have subtle effects on the solar system and Earth's environment, though the magnitude of any such effects is debated among astronomers. While density wave theory explains many features of spiral arms, astronomers now believe the full picture is more complex than the simple models of the 1960s. Different models have been proposed and debated. The Grand Design model suggests long, tightly wound spiral arms created by density waves sweeping through the disk. The multi-arm model proposes multiple arm segments that aren't fully connected into continuous spirals. The flocculent model suggests many short arm segments rather than coherent spiral arms, giving the galaxy a patchy, fluffy appearance. The Milky Way appears to be an intermediate case, with both large-scale spiral structure driven by density waves and the central bar, and smaller-scale features created by local gravitational instabilities. The interaction with satellite galaxies may also influence the arms, perturbing them and potentially triggering new arm segments. The galactic magnetic field is stronger in spiral arms than in the regions between arms. As gas flows into a spiral arm, it compresses not only the matter, but also the magnetic field lines threaded through it, bunching them together and increasing the field strength. This compressed magnetic field affects star formation in complex ways. It provides pressure support that resists the gravitational collapse of gas clouds, potentially slowing star formation. But it can also channel gas flows and shape collapsing clouds. The magnetic field also influences the motion of charged particles and cosmic rays, effectively trapping them in the galaxy. Observations at radio wavelengths, which are sensitive to synchrotron radiation from electrons spiraling in magnetic fields, clearly show the spiral arm structure of the galaxy, demonstrating the important role of magnetic fields in galactic structure and dynamics. Astronomers use several types of objects as tracers to map the spiral arms, since we can't step outside the galaxy to photograph it directly. Young, massive blue stars are excellent tracers because they're extremely bright, visible across great distances, and remain near where they were born. Regions of ionized hydrogen gas, called HE2 regions, which glow pink or red in the light of embedded hot stars, also trace spiral arms beautifully. Giant molecular clouds, dense concentrations of cold molecular hydrogen gas, are found primarily in spiral arms where star formation occurs. Radio sources called masers, which are like naturally occurring lasers, but operating at microwave frequencies and often associated with star-forming regions, also mark the arms. By mapping these various tracers and combining the observations, astronomers have pieced together a map of the Milky Way's spiral structure, though uncertainties remain about the exact number of arms and their precise shapes. The regions between spiral arms, called inter-arm regions, are not completely empty. There are still plenty of stars there, but at lower densities than in the arms. These inter-arm regions contain primarily older stellar populations, stars that have drifted out of the spiral arms where they were born, or stars that formed during earlier epochs when the spiral pattern was different. Gas is present but less abundant, and star formation is less active or completely absent. Our solar system currently resides in such an inter-arm region, which may have implications for Earth's history and the development of life. The rate of nearby supernova explosions is lower in inter-arm regions, reducing the radiation hazards that might affect planetary atmospheres and life. Some researchers have speculated that being in an inter-arm region for much of Earth's history may have been favorable for the development and survival of complex life. Spiral arms are not static features, frozen in place in the galaxy. They can change over time, strengthening, weakening, and even reforming in different configurations. Computer simulations of galactic dynamics show that spiral patterns can be transient on timescales of hundreds of millions to a few billion years. Arms can form through gravitational instabilities in the disk, persist for a significant time, then gradually dissolve, only to reform again later, possibly in a different configuration. The presence of the central bar strongly influences the spiral structure, with the bar helping to maintain and shape the arms. The bar itself may form and dissolve over cosmic time as well, though on timescales of billions of years. Interactions with satellite galaxies can trigger or enhance spiral structure. with the gravitational perturbation from a passing dwarf galaxy sending waves through the disk that manifest as spiral arms. Over the Milky Way's 13 billion year history, its spiral arms have likely evolved significantly, though they may have been a persistent feature for billions of years. As stars orbit the galaxy, their paths carry them through spiral arms, and the arms exert gravitational forces on the passing stars. These gravitational interactions don't significantly change a star's orbit on a single pass. The forces are too small and act for too short a time. But over many orbits, over billions of years, the cumulative effects can gradually alter stellar orbits. This is one mechanism by which stars initially on circular orbits in the galactic plane can be scattered into more elliptical orbits or kicked above and below the plane. The spiral arms thus act as gravitational stirrers, slowly heating the disk over cosmic time. Astronomers use the technical term heating to mean increasing the random velocities of stars, making their orbits less circular and more elliptical. This process gradually thickens the disk over billions of years, as stars are scattered into orbits that carry them higher above and below the galactic plane. The Sun orbits the galactic center in a roughly circular path at a distance of about 26,000 light-years from the center. One complete orbit takes 225 to 250 million years, our galactic year. The Sun's orbital velocity is about 220 kilometers per second relative to the galactic center. That's over 790,000 kilometers per hour, nearly 1,000,000 kilometers per hour. Despite this tremendous speed, we don't feel the motion at all, because everything in our vicinity, the Sun, all the planets, nearby stars, the gas and dust around us, is moving together in the same direction at roughly the same speed. It's like sitting in a smoothly moving train. You don't feel the motion unless you look outside at the passing scenery, or unless something causes the train to change speed or direction. While orbiting the galaxy in the disk, the Sun also bobs up and down through the galactic plane, oscillating above and below the midplane like a horse on a cosmic carousel. Currently, the solar system is about 52 light-years above the galactic plane and moving upward at about 7 kilometers per second. We'll continue moving upward for another 10 or 15 million years before gravity pulls us back down. The Sun completes about 3 or 4 of these vertical oscillations during each galactic orbit, with a period of approximately 64 million years for each up and down cycle. This oscillation is caused by the gravitational pull of matter in the galactic disk. As the Sun moves above the plane, the gravity of all the stars and gas in the disk below pulls it back down. It accelerates as it falls, gaining speed, then shoots through the plane and overshoots to the other side due to its momentum, then is pulled back again, creating a continuous bobbing motion that will continue for as long as the Sun exists. Not only does the Sun oscillate vertically through the disk, but it may also have migrated radially over its lifetime, moving closer to or farther from the galactic center. This radial migration can occur through gravitational interactions with spiral arms, massive molecular clouds, and other structures in the disk. When a star passes through a spiral arm, the gravitational interaction can either speed it up or slow it down slightly, depending on the details of the encounter. Slowing down causes a star to fall inward to a smaller orbit. Speeding up causes it to move outward to a larger orbit. Over many passages through spiral arms and encounters with clouds over hundreds of millions of years, stars can migrate significant distances. Some simulations suggest the Sun may have formed closer to the galactic center, perhaps at a distance of only 20 to 22,000 light years, and gradually migrated outward to its current position. Alternatively, it could have formed farther out and migrated inward. This migration would have carried the solar system through regions of the galaxy with different stellar densities, supernova rates, and environmental conditions, potentially affecting Earth's history in subtle ways. The Sun formed 4.6 billion years ago in a giant molecular cloud, probably within a star cluster containing hundreds or thousands of other stars, all born from the same cloud at roughly the same time. These stars were siblings, born together, initially orbiting each other in a loose cluster. But all those sibling stars have long since dispersed, scattered across the galaxy by gravitational interactions within the cluster, encounters with other clusters, and interactions with the galaxy's tidal forces and spiral arms. The Sun's siblings are now spread throughout the galaxy, indistinguishable from other stars formed at different times and places. However, astronomers are searching for solar siblings, stars with similar ages and, more importantly, very similar chemical compositions that might have formed in the same molecular cloud. If stars formed from the same cloud, they should have essentially identical abundances of different elements, like a chemical fingerprint. A few candidates have been identified, but confirming they're truly siblings is difficult and requires very precise measurements. As the Sun orbits the galaxy, it occasionally passes relatively close to other stars. Currently, the closest star to the Sun is Proxima Centauri, part of the Alpha Centauri system, about 4.2 light-years away. In the denser regions of the galactic disk, stellar encounters occur more frequently. Every few 100,000 years on average, another star passes within about 1 light-year of the Sun. Every few million years, a star might pass within half a light-year. These passages are generally not close enough to significantly affect the planet's orbits around the Sun. The planets are bound too tightly to the Sun to be easily disrupted. However, such stellar encounters can disturb the Oort cloud, a vast swarm of comets surrounding the solar system in a spherical shell extending perhaps halfway to the nearest stars. Gravitational perturbations from passing stars can send comets falling toward the inner solar system, potentially increasing the rate of cometary impacts on Earth. Some researchers have speculated that some mass extinctions in Earth's history might have been triggered or influenced by increased comet bombardment following stellar encounters, though this remains controversial. The solar system takes about 2 million years to cross through a spiral arm during its galactic orbit. During these passages, the solar system moves through regions of higher stellar density and more active star formation. This means more massive stars in the vicinity, and massive stars eventually explode as supernovae. Some researchers have speculated that passages through spiral arms might be associated with increased supernova rates near Earth, potentially affecting Earth's atmosphere and climate, or even contributing to mass extinctions. The theory suggests that nearby supernovae could produce cosmic rays and radiation that affect the atmosphere, potentially depleting the ozone layer or affecting cloud formation and climate. However, the evidence for these effects is controversial, and most astronomers think the effects, if they exist at all, are likely subtle. The dates of spiral arm crossings don't match up well with the dates of known mass extinctions, and the expected radiation doses are probably too small to cause major biological damage. Just as there's a habitable zone around a star where planets can have liquid water, some researchers have proposed the concept of a galactic habitable zone, a region of the galaxy where conditions are favorable for the development of life and technological civilizations. Too close to the galactic center, there's intense radiation from the supermassive black hole and surrounding sources, frequent supernova explosions due to high stellar density, and close stellar encounters that might disrupt planetary systems. Too far out in the outer regions of the galaxy, there may be insufficient heavy elements, carbon, oxygen, nitrogen, and others, to form terrestrial planets and the chemistry of life, since these elements are produced by previous generations of stars. The Sun's location, about halfway out from the center, in the disk but between major spiral arms, is thought to be within this galactic habitable zone. However, the concept remains speculative, and life might be more resilient and adaptable than we imagine, potentially thriving in a wider range of galactic environments than we currently think possible. Over the next few billion years, the Sun will continue on its orbit around the galaxy, passing through spiral arms, bobbing above and below the galactic plane, and possibly gradually migrating to a different orbital radius. But there's a major event on the horizon that will dramatically change everything. In about 4 to 5 billion years, the Milky Way will collide and merge with the Andromeda Galaxy. Long before the actual collision, the galaxy's gravitational interaction will begin to affect stellar orbits throughout both galaxies. The Sun's future path through the galaxy will be altered by this impending collision. Though predicting exactly how is extremely difficult, given the complex many-body dynamics involved. The Sun might be flung into the outer regions of the merged galaxy, or even ejected entirely into intergalactic space, though the latter is unlikely. Since the Sun and Solar System formed 4.6 billion years ago, the Sun has completed approximately 20 orbits around the galaxy, 20 galactic years. Each orbit has carried the Solar System through different regions of the galaxy, exposing Earth to varying environmental conditions, though how much these variations affected Earth's history is uncertain. The first galactic orbit occurred when Earth was still molten, being bombarded by impacts from leftover debris of the Solar System's formation. By the fifth or sixth galactic orbit, around 3 billion years ago, life had emerged in Earth's oceans, though only simple single-celled organisms. Around the 10th orbit, perhaps 2 billion years ago, more complex cells with nuclei, eukaryotes, were developing. By the 15th orbit, multicellular life was emerging. Around the 18th orbit, 500 million years ago, plants and animals had colonized the land, and the Cambrian explosion of diverse life forms was in full swing. Dinosaurs rose and fell during the 19th and 20th orbits. Human civilization, all of recorded history, has emerged in just the last tiny fraction of our current 20th galactic orbit, in the blink of an eye on galactic timescales. From Earth, we see a band of light across the night sky. the combined light of billions of stars in the galactic disk. The Milky Way is best seen from dark locations far from city lights, in regions free from light pollution. The brightest and widest part of the band is towards Sagittarius, where we're looking toward the galactic center through the dense star fields of the central bulge. The faintest part is in the opposite direction, toward the constellations Auriga and Taurus, where we're looking away from the center toward the outer, less populated regions of the galaxy. Dark rifts visible within the Milky Way are not gaps in the stars, but rather dust clouds in the foreground that block the light of stars beyond. Every culture that has lived under dark skies has noticed this band of light stretching across the heavens and incorporated it into their mythology and cosmology. Aboriginal Australians saw the dark rifts as a celestial emu. The ancient Chinese called it the Silver River. We are, quite literally, living inside the Milky Way, looking at our home galaxy from within, seeing it edge on from our position in the disk. Surrounding the galactic disk is a roughly spherical halo of old stars extending perhaps 130,000 light-years or more from the center, larger than the visible disk itself. This stellar halo contains only about 1% of the galaxy's stars, so the density of stars in the halo is very low compared to the disk, perhaps 1 star per 10,000 cubic light-years, or even more sparse. Halo stars have highly elliptical orbits that carry them far above and below the galactic plane, sometimes reaching distances of 100,000 light-years or more, then plunging back down through the disk. They move on ballistic trajectories, like cannonballs shot in various directions, their paths shaped entirely by the galaxy's gravitational field. These are very old stars, typically 10 to 13 billion years old, formed in the early history of the galaxy when the universe itself was young and quite different from today. The halo contains approximately 150 globular clusters, ancient spherical collections of stars that rank among the most spectacular objects visible through telescopes. Each globular cluster contains hundreds of thousands to millions of stars gravitationally bound into a spherical swarm. Globular clusters are among the oldest objects in the galaxy, with ages of 12 to 13 billion years, formed when the Milky Way itself was still assembling. They orbit the galaxy in the halo on highly elliptical paths that take them far from the galactic center, out to distances of 100,000 light-years or more, and then back in, sometimes passing through the disk. The clusters are gravitationally bound systems, held together by the mutual gravitational attraction of their stars. In the dense cores of globular clusters, stars are packed so tightly that the average separation is only about 1 light-year compared to over 4 light-years between the Sun and its nearest neighbor. If Earth were located in the core of a globular cluster, the night sky would be spectacular, filled with hundreds of stars brighter than Sirius, the brightest star in our sky. Stars in the halo are remarkably metal-poor. In astronomical terminology, metals means all elements heavier than hydrogen and helium. Halo stars have much lower abundances of heavy elements compared to the Sun and other disk stars, sometimes by factors of 100 or even 1,000. Some halo stars have iron abundances just 1/10,000th that of the Sun. This metal-poor composition is one line of evidence that these stars are very old, formed early in the galaxy's history before many generations of stars had lived and died, enriching the interstellar medium with heavy elements produced in their cores and supernova explosions. The first generation of stars in the universe, formed from the pristine material produced by the Big Bang, would have contained only hydrogen, helium, and trace amounts of lithium. Studying metal-poor halo stars gives astronomers clues about the early universe and the chemical evolution of the galaxy over billions of years. Crisscrossing the halo are stellar streams, long, thin trails of stars stretched out along their orbits. These streams are the remnants of disrupted satellite galaxies and globular clusters that were torn apart by the Milky Way's powerful tidal forces. As a satellite galaxy orbits the Milky Way, tidal forces, differences in gravitational pull across the satellite due to its finite size, gradually pull the satellite apart. Stars are stripped from the satellite, first from the near and far sides where tidal forces are strongest, and spread out along the satellite's orbit in front of and behind the doomed galaxy. Over hundreds of millions of years, the satellite is completely shredded, its stars forming a long stream wrapping around the Milky Way, sometimes multiple times. Many stellar streams have been discovered in recent years through careful surveys of star positions and velocities. These streams provide evidence for the hierarchical buildup of the Milky Way, the idea that our galaxy grew by absorbing smaller systems over cosmic time, gradually assembling from smaller building blocks. One of the most prominent stellar streams comes from the Sagittarius dwarf elliptical galaxy, a small satellite galaxy currently in the process of being torn apart by the Milky Way's gravity. Discovered in 1994, this dwarf galaxy is on the opposite side of the galactic center from Earth, about 65,000 light-years away, behind the central bulge which had hidden it from view. As it orbits the Milky Way, it's leaving behind long streams of stars that wrap around our galaxy. Observations suggest that the Sagittarius dwarf has already made several passes through the Milky Way's disk, passing through once every billion years or so, and each passage strips away more of its stars. These interactions may have triggered disturbances in the disk, including possible vertical ripples or warps. The Sagittarius dwarf will continue to be pulled apart over the next billion years until it's completely dissolved, its stars joining the Milky Way's halo. The stellar halo is ancient, formed during the galaxy's early history through a combination of processes. Some halo stars formed in the galaxy itself when it was young, before the disk had fully settled and star formation had moved into the plane. Other halo stars were brought in as part of satellite galaxies that fell into the Milky Way and were disrupted, their stars scattered into the halo. Most halo stars are at least 10 billion years old, and the oldest may be nearly 13 billion years old, almost as old as the universe itself, formed within the first billion years after the Big Bang. These ancient stars are like fossils from the galaxy's formation epoch, carrying information about conditions in the early Milky Way in their chemical compositions and orbital properties. The chemical composition, orbits, and distribution of halo stars provide crucial clues about how the galaxy formed. The evidence suggests the halo was built up over time through the accretion of many smaller systems, dwarf galaxies, and star clusters that fell into the Milky Way and were disrupted, a process that continues today. Orbiting the Milky Way are dozens of dwarf satellite galaxies, small galaxies containing anywhere from millions to billions of stars. The largest and most famous are the Large and Small Magellanic Clouds, irregular dwarf galaxies clearly visible from the southern hemisphere as large, fuzzy patches in the sky. These satellites contain billions of stars and are currently being distorted by the Milky Way's tidal forces, slowly being pulled apart. Closer to the Milky Way are many ultra-faint dwarf galaxies containing only thousands to hundreds of thousands of stars. These ultra-faint dwarfs are incredibly difficult to detect. They're so dim that they're barely distinguishable from random clusterings of foreground stars. New ones are still being discovered as astronomical surveys become deeper and more sophisticated. These ultra-faint dwarfs may be the most dark matter-dominated objects in the universe, with dark matter outweighing visible stars by factors of hundreds or even thousands, making them important laboratories for studying the nature of dark matter. Over cosmic time, the Milky Way has been continuously consuming its satellite galaxies in a process astronomers sometimes call galactic cannibalism. Gravitational tidal forces gradually tear apart these smaller systems over hundreds of millions to billions of years, and their stars join the Milky Way's halo or disk. Computer simulations suggest that most of the halo was built up through this process of accretion and disruption. Even now, this process continues in real time, though slowly by human standards. The Sagittarius dwarf is being actively disrupted, losing stars with each orbital passage. The Magellanic Clouds will eventually be absorbed over the next few billion years, though they may merge with each other first before being consumed by the Milky Way. These mergers are a key aspect of galactic evolution in the universe. Galaxies grow by eating their smaller neighbors, a process predicted by theories of structure formation in the universe and observed throughout the cosmos. The halo is dominated by dark matter, though it contains relatively few visible stars, while the visible stellar halo contains only a small fraction of the galaxy's stars. The dark matter halo contains most of the galaxy's total mass. This dark matter extends far beyond the visible stars, perhaps several 100,000 light-years from the galactic center, possibly even further. The dark matter's gravitational pull dominates the motions of halo stars, globular clusters, and satellite galaxies. In the dwarf satellite galaxies, dark matter can outweigh visible matter by extraordinary ratios, factors of hundreds or thousands to one. A dwarf galaxy might contain only a few million visible stars, but be embedded in a dark matter halo, weighing billions of solar masses. These small satellites are important laboratories for studying dark matter because its effects are so pronounced and because competing theories of gravity make different predictions for the behavior of these systems. Scattered through the halo are a few stars moving at extreme velocities, fast enough to escape the Milky Way's gravitational pull entirely. These hypervelocity stars are traveling at speeds exceeding 500 kilometers per second, some even faster than 700 kilometers per second, on trajectories that will carry them out of the galaxy into the vast emptiness of intergalactic space. How did they get moving so fast? Most hypervelocity stars are thought to have been accelerated by gravitational encounters with the supermassive black hole at the galactic center. A binary star system, two stars orbiting each other, strays too close to Sagittarius A. The intense tidal forces and gravitational interactions tear the binary apart. One star is captured into orbit around the black hole, while the other is flung outward at tremendous speed, like a stone from a cosmic slingshot. These stellar exiles will eventually leave the Milky Way forever, becoming isolated travelers wandering through the space between galaxies, slowly fading over trillions of years, never to return to their home galaxy. The Milky Way's nearest large galactic neighbor is the Andromeda Galaxy, also known as Messier 31 or M31, located about 2.5 million light-years away. Andromeda is a spiral galaxy somewhat larger than the Milky Way, containing perhaps 1 trillion stars compared to our few hundred billion. It's the most distant object visible to the unaided human eye. On a dark night, far from city lights, Andromeda appears as a faint, fuzzy oval patch in the constellation Andromeda. Despite the immense distance separating us, 2.5 million light-years, a gulf so vast that light takes 2.5 million years to cross it, Andromeda is approaching the Milky Way at about 110 kilometers per second. Rather than moving apart as most galaxies in the universe are due to cosmic expansion, the Milky Way and Andromeda are moving toward each other, pulled together by their mutual gravitational attraction. A collision is inevitable. It's not a question of if, but when. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide. However, collision is something of a misnomer that conjures images of catastrophic destruction. When galaxies collide, the stars themselves almost never hit each other. The distances between stars are so vast compared to their sizes that they pass by each other like two swarms of gnats interpenetrating without individual insects colliding. If the sun were the size of a grain of sand, remember, the nearest star would be another grain of sand 10 kilometers away. The chances of two stars actually colliding during a galactic merger are astronomically small. What does collide violently is the gas in the two galaxies. When giant gas clouds collide at speeds of hundreds of kilometers per second, they compress and heat dramatically, triggering intense bursts of star formation throughout both galaxies. The collision will dramatically alter both galaxies, scrambling their orderly structures and potentially triggering spectacular displays of star birth unseen in either galaxy for billions of years. The collision won't be a single event, but rather a long, complex process lasting billions of years, unfolding in slow motion by human standards, but rapid on cosmic timescales. The first close passage will occur in about 4 billion years. At that point, the two galaxies will swing past each other, their gravitational interaction pulling out long tidal tails, streams of stars drawn from each galaxy by the other's gravity, stretching across hundreds of thousands of light years. The galaxies will separate briefly after this first encounter, but gravity will pull them back together for second and third close passages over the next billion years. Each passage will be more violent than the last, with more stars and gas torn from each galaxy. Eventually, perhaps a billion years after the first encounter, the two galaxies will merge completely, their contents mixing together to form a single, larger galaxy. The merger will convert two majestic spiral galaxies into a single, giant elliptical galaxy. The ultimate result of the Milky Way Andromeda collision will be a single giant elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda by astronomers. This new galaxy will be quite different from the two spiral galaxies that formed it. It will have a more spherical or elliptical shape rather than a flat disk with spiral arms. The orderly rotation of the spiral galaxies will be replaced by more random stellar orbits. Most of the gas in both galaxies will have been consumed in a final, intense burst of star formation during the merger, triggered by the violent compression of gas clouds as the galaxies interpenetrate. After this starburst subsides, little gas will remain for future star formation. The merged galaxy will gradually age and redden over billions of years as its stars evolve, with fewer and fewer young blue stars to replace the ones that die. The merged galaxy will be larger than either of its parent galaxies, containing the combined mass of both, perhaps 1.5 trillion solar masses of stars, gas, and dark matter. What will happen to the solar system during this galactic collision? The Sun and Earth will almost certainly survive the merger. As we've discussed, the chances of a direct collision with another star are extremely small, even during the chaos of a galactic merger. The solar system will be buffeted by gravitational forces as the galaxies interact, but the Sun's grip on its planets is strong enough to hold them. However, the Sun's orbit around the galactic center will be drastically altered by the merger. The solar system might be flung into the outer regions of the merged galaxy, perhaps 50,000 or even 100,000 light-years from the new center. Alternatively, it might be scattered into the newly formed halo, or in a less likely but possible scenario, even ejected from the galaxy entirely to wander in intergalactic space. The night sky as seen from Earth will be dramatically different after the merger, with the stars of both galaxies mixed together in new configurations, and perhaps a close-up view of the central regions of the newly formed elliptical galaxy, blazing with billions of stars. The galactic collision will occur at roughly the same time the Sun faces its own crisis, adding cosmic irony to the situation. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. Having fused hydrogen into helium for billions of years, it will begin fusing helium into carbon and oxygen in its core, while hydrogen fusion continues in a shell around the core. The Sun will swell dramatically, expanding to perhaps 100 times its current diameter, becoming a red giant star. Its outer layers will extend past the orbit of Mercury, possibly past Venus, perhaps even engulfing Earth itself. Even if Earth's orbit expands enough to avoid being physically engulfed, which is uncertain, the planet will be scorched, its oceans boiled away, its atmosphere stripped, transformed into a lifeless cinder. After the red giant phase, lasting perhaps 1 billion years, the Sun will shed its outer layers in a beautiful planetary nebula, leaving behind a white dwarf remnant, a dense, hot core about the size of Earth, but containing about half the Sun's current mass, slowly cooling over trillions of years. So the solar system will be facing its own transformation at the same time the galaxy is merging with Andromeda. Looking billions of years beyond the Andromeda merger, the Milky Way's remnant, the merged Milky Way Galaxy, will continue to evolve. Star formation will gradually cease over tens of billions of years as the gas supply is exhausted and no new gas falls in from outside. One by one, stars will die. Massive stars, which live only millions of years, will have long since disappeared, having exploded as supernovae billions of years earlier. Medium mass stars like the Sun will die over the next few billion to tens of billions of years, becoming white dwarfs. The lowest mass red dwarf stars, which live for trillions of years, will still be shining long after all other stars have died. Eventually, perhaps 10 trillion years from now, 10,000 billion years, even the longest-lived red dwarfs will exhaust their fuel and fade to black dwarfs. The galaxy will contain only stellar remnants, white dwarfs, neutron stars, and black holes, along with failed stars like brown dwarfs, wandering planets, and the cold molecular clouds of leftover gas. The galaxy will be dark, a ghost of its former self, slowly dispersing as stars occasionally acquire enough energy through chance encounters to escape to intergalactic space. The Milky Way and Andromeda are the two largest members of the local group, a collection of about 50 galaxies bound together by gravity, spanning about 10 million light years. When the Milky Way and Andromeda merge, they'll form the dominant member of the local group, containing most of the group's total mass. Over the billions of years following the merger, the merged Milky Way Galaxy will gradually consume other local group members. The Triangulum Galaxy, M33, the third largest group member, will likely merge with Milky Way sometime after the Milky Way Andromeda collision, adding its 50 billion or so stars to the mix. Small dwarf galaxies will be tidally disrupted and accreted over time. Eventually, billions of years hence, the local group may become a single giant elliptical galaxy, having consumed all its members, an isolated island of stars in an increasingly empty universe. While the Milky Way and Andromeda are coming together, and the local group will eventually merge, the universe as a whole is expanding, and this expansion is accelerating, driven by dark energy. This acceleration is one of the most profound discoveries in modern cosmology. Dark energy is a mysterious property of space itself, possibly related to the energy of the vacuum, causing space to expand at an ever-increasing rate. On small scales, within galaxy clusters like the local group, gravity is strong enough to overcome the expansion, holding structures together and even pulling them together to merge. But on larger scales, dark energy dominates. Eventually, in the distant future measured in hundreds of billions of years, dark energy's repulsive effect will dominate over gravity on increasingly smaller scales. Galaxy clusters beyond the local group are already being carried away by the accelerating expansion, gradually disappearing beyond our cosmic horizon as they recede faster than light can travel. The merged Milky Way Galaxy and the local group remnant will find themselves increasingly isolated in an ever-emptying observable universe. Looking far into the future, trillions upon trillions of years from now, the universe will be vastly different from the cosmos we see today. Star formation will have ceased throughout the universe as gas is exhausted and existing stars die. Galaxies will be dark assemblages of stellar remnants, wandering through an increasingly empty space. Eventually, even these remnants will disappear through various processes. White dwarfs will cool to black dwarfs over tens of trillions of years. If protons are unstable, as some theories suggest, though this remains unproven, even these dense remnants will eventually decay into radiation and lighter particles over timescales of 10 to the 36 years or more, timescales so vast they defy human comprehension. Black holes will be among the last objects to survive, but even they are not eternal. Through a quantum process called Hawking radiation, predicted by Stephen Hawking, black holes slowly evaporate, radiating away their mass as particles and radiation over timescales that depend on their mass. Stellar mass black holes will evaporate in 10 to the 67 years or so. Supermassive black holes, like Sagittarius A, will take even longer, perhaps 10 to the 100 years, a 1 followed by 100 zeros, to completely evaporate. Eventually, the universe will approach a state of maximum entropy, the heat death of the universe, cold, dark, and nearly empty, with only isolated particles separated by vast distances in an ever-expanding space. The distant future may seem bleak from our current perspective, but it's worth remembering that these timescales are so vast as to be nearly meaningless. 10 trillion years, the time until the last red dwarf stars die, is more than 700 times the current age of the universe. 10 to the 100 years, the lifetime of supermassive black holes, is a timescale so vast that there are more ways to arrange a deck of cards than there are seconds in that time. By any reasonable standard, the universe has plenty of life left in it. Stars will continue forming and shining for trillions of years. Planets will continue orbiting their suns. And perhaps life and intelligence will continue to exist, adapt and evolve, spreading throughout the cosmos, finding ways to survive even as the universe grows old and cold around them. The Milky Way, along with everything it contained, including our solar system and Earth, will have transformed beyond recognition over these vast timescales. The atoms that currently make up our bodies, our world, our sun, will have been scattered and reformed countless times. They may be part of future stars in the merged Milky Way Galaxy. They may be incorporated into planets orbiting those stars. They may drift in the interstellar medium, cold and dark. They may eventually be consumed by black holes, and much later be radiated away as Hawking radiation. Yet even in that unimaginably distant future, those atoms will carry within them a connection to this moment, to the Milky Way as it exists now, to Earth, to us. We are temporary patterns in the flow of matter and energy through the cosmos, but we are part of that flow, part of the universe's story, part of the long chain of cause and effect stretching from the Big Bang to the far future. As we conclude our journey through 100 facts about the Milky Way, we're reminded of the extraordinary nature of our cosmic home. This vast spiral of stars spanning 100,000 light-years of space, containing hundreds of billions of suns, countless planets, mysterious dark matter, and a supermassive black hole at its heart, is the galaxy we call home. From its formation nearly 14 billion years ago, just 200 million years after the Big Bang itself, to its eventual merger with Andromeda billions of years in the future, the Milky Way has been and will continue to be a dynamic, evolving structure, changing over cosmic time even as it maintains its essential character as a spiral galaxy. It's a place of incredible beauty and profound mystery. From the supermassive black hole at its heart, Sagittarius A, containing over 4 million times the mass of our Sun, compressed into a region smaller than our inner solar system, to the faint, ancient stars in its distant halo, formed when the universe was young and carrying within them the chemical signatures of the earliest stellar generations. From the bright spiral arms where new stars are continuously being born in glowing nebulae, to the dark matter that holds everything together through invisible gravitational threads. Comprising 90% of the galaxy's mass, yet remaining completely invisible to our telescopes, we are creatures of the Milky Way, born from it and shaped by it. Every atom in our bodies was forged in the hearts of stars that lived and died within this galaxy. The oxygen we breathe with every breath, created in the cores of massive stars and scattered into space when they exploded as supernovae. The calcium in our bones also formed in stellar furnaces. The iron in our blood that carries oxygen through our bodies, forged in the final seconds of supernova explosions. The carbon that forms the backbone of every organic molecule in our bodies, fused from helium in the cores of dying stars. We are made of star stuff, as Carl Sagan memorably said. We are the Milky Way made conscious, the universe aware of itself, matter contemplating its own existence and origins. As we orbit quietly in our suburban location, 26,000 light-years from the galactic center, nestled in the Orion spur between the larger Perseus and Sagittarius spiral arms, we're part of this vast cosmic structure. Our solar system is just one small part of the Milky Way, one star among hundreds of billions, one planetary system among perhaps trillions. Yet from our vantage point, limited though it is by our position inside the galaxy, we can study and appreciate the entire structure. Through centuries of patient observation, clever inference, and increasingly sophisticated technology, we've mapped our galaxy, measured its properties, traced its history, and predicted its future. We've discovered that we live in a galaxy that's part of a much larger structure, the local group of galaxies, which is itself part of the Virgo supercluster, a vast assemblage of thousands of galaxies stretching across tens of millions of light years. We've learned that our galaxy formed through the gradual assembly of smaller structures, growing over billions of years by consuming smaller galaxies, a process that continues today as we slowly tear apart the Sagittarius dwarf and other satellite galaxies. We've found that the Milky Way is not static, but dynamic, with stars continuously forming in some regions while dying in others, with gas flowing inward to fuel star formation and flowing outward in winds driven by dying stars, with spiral arms forming and dissolving over hundreds of millions of years, with the central bar channeling material toward the galactic center, with the entire structure rotating differentially, with stars and gas moving in complex patterns shaped by gravity, magnetic fields, and the pressure of radiation and cosmic rays. We've discovered that most of what makes up our galaxy is invisible, dark matter whose nature remains one of the greatest mysteries in modern science. We don't know what it's made of. We can only detect it through its gravitational effects. Yet it dominates the galaxy's mass and determines the motions of stars and gas throughout the Milky Way. Solving the mystery of dark matter remains one of the great challenges for 21st century astronomy and physics. We've learned that at the galaxy's heart lies an object that challenges our understanding of space, time, and matter, a supermassive black hole where the fabric of space-time is warped to extremes, where matter is compressed to infinite density, where the laws of physics as we know them break down. Yet this monster at the center, rather than being merely destructive, may play a crucial role in regulating the galaxy's evolution. its past activity shaping the galaxy we see today. We've found that our location in the galaxy, our place in space and time, may have been important for our existence. Located between spiral arms, where supernova explosions are less frequent, in a region with enough heavy elements to form rocky planets, but not so many that the night sky is ablaze with nearby stars, and the radiation environment is hostile. At a time when the sun is stable and middle-aged, with several billion years still ahead of it. On a planet in the habitable zone, with liquid water and a protective atmosphere. These circumstances, which may seem like coincidences, may actually have been necessary for complex life to evolve and for intelligence to emerge. We've contemplated the future, both near and distant, the eventual collision and merger with Andromeda in 4 to 5 billion years, transforming our spiral galaxy into an elliptical one, mixing together the stars of two galaxies. The far future, trillions of years, hence, when star formation will cease and galaxies will slowly fade and disperse. The ultimate fate of matter itself as black holes evaporate and the universe approaches maximum entropy. These futures, both certain and speculative, remind us of the temporary nature of all structures in the universe, yet also of the vast timescales on which the cosmos operates. Throughout this journey, we've been reminded repeatedly of the scales involved, scales of space, of time, of mass and energy that dwarf human experience and challenge our ability to comprehend. Light years and parsecs, distances so vast that light itself takes years to cross them. Billions and trillions of stars, numbers so large they lose meaning. Ages measured in billions of years, timescales compared to which human civilization is a brief flicker. Masses measured in solar masses, energies measured in supernovae, temperatures measured in millions of degrees. Yet despite these overwhelming scales, here we are, on a small rocky planet orbiting an ordinary star in a quiet suburb of an ordinary spiral galaxy, able to comprehend all of this. Able to measure the distances to stars, to determine the galaxy's shape and size, to detect the presence of invisible dark matter through its gravitational effects, to infer the existence of a supermassive black hole at the galactic center by watching stars orbit around it, to predict the future collision with Andromeda billions of years hence. This ability to understand our place in the cosmos, to grasp scales far beyond direct human experience, to trace our origins back to the Big Bang and predict the ultimate fate of the universe, is perhaps humanity's greatest achievement. The Milky Way is our home on the largest scales we can meaningfully conceive. Not just Earth, not just the solar system, but the entire galaxy is our home environment, the stage on which the story of humanity and Earth has played out. The same processes that formed the Milky Way, the collapse of gas under gravity, the formation of stars, the synthesis of heavy elements in stellar cores, the scattering of those elements into space by dying stars. These processes created the material from which our world and our bodies are made. When we look up at the Milky Way on a dark night, we're seeing our galaxy from the inside, looking through countless stars to the distant reaches of the galactic disk. We're seeing light that left those stars decades, centuries, or millennia ago. Light that has traveled across vast distances to reach our eyes. We're looking at our extended cosmic home, the stellar city in which we live, the island of stars that is our galaxy in the vast ocean of the universe. Whether you listen to this to fall asleep, to study, to relax, or simply to learn more about the universe and our place in it, we hope these 100 facts have deepened your appreciation for the Milky Way, our island in the infinite ocean of the cosmos. We hope you've gained a sense of the scale, complexity, beauty, and mystery of our galactic home. We hope you felt a connection to the cosmos, a recognition that we are part of something vast and ancient and ongoing, that we are participants in the grand cosmic story that began with the Big Bang and continues today. As you go about your daily life, remember that you're on a planet orbiting a star that orbits the center of a galaxy, moving through space at hundreds of kilometers per second. Remember that you're made of atoms, forged in the hearts of ancient stars. Remember that you're part of the Milky Way, and the Milky Way is part of you. Remember that we live in an extraordinary universe, in an extraordinary galaxy, at an extraordinary time when we can begin to understand our cosmic origins and our place in the vastness of space and time. Thank you for joining us on this journey through the Milky Way Galaxy. May you rest well under the stars, and may your dreams carry you through the spiral arms of our cosmic home, past the supermassive black hole at the center, out to the ancient globular clusters in the halo, and forward in time to the distant future when our galaxy merges with Andromeda, transforming into something new, yet still carrying within it the legacy of the Milky Way as it exists today. Look up at the night sky when you can. Find a dark place far from city lights. Let your eyes adjust to the darkness and see the Milky Way stretching across the heavens. A river of light, our home among the stars, clear skies,